Okay, so let's start today's lecture. What we had done last time was to show that if we have a primitive solvable extension of some field F, the extension is called E, then the Galois closure E hat of E over F is of a special kind. And what special kind? Well, the Galois group of E hat over F has a unique minimal normal subgroup. And that is, so if the degree of E over F is L to the N, this is something which we had proved earlier. I mean, Galois himself had proved that the degree of a primitive solvable extension is a prime power. So suppose that the degree of E over F is L to the N, where L is a prime. Now, when you go to the Galois closure E hat, the minimal normal subgroup of the Galois group of E hat over F is going to be Z mod LZ to the power N. It's going to be isomorphic to this elementary abelian L group. Okay. Moreover, the invariance under this is an extension K of F, let's call it K, right? So what do we know about K? What we know is that the Galois group of E hat over K, which is of course the same as N, the minimal normal subgroup of the Galois group of E hat over F, is a faithful simple module over the Galois group of K over F, right? Let me use this here. Maybe it's working. I don't know. Yeah, here. Yes. So you have N is the minimal normal subgroup of the Galois group of E hat over F. And it turns out to be it's an FL space of dimension N, first of all. And it's a faithful simple module over the Galois group of K over F, where K is the fixed field of N. Okay? So now what I want to say is that given this E over F, I get a pair E hat, rho E, comma E hat. So let me explain E hat. I've already told you what it is. Let me tell you what rho E is, right? So now the Galois group of K over F, of course, acts upon the Galois group of, where is it? It acts upon N. It acts upon the Galois group of E hat over K, because you have this exact sequence, right? And this Galois group of K over F is also, of course, a quotient of the absolute Galois group. It's a quotient. Where's the absolute Galois group? It's here. It's a quotient of this absolute Galois group. And this acts on N. So ultimately, I get a representation of this absolute Galois group on N. And it can be checked that it's a faithful. It's not faithful, of course. When you go to the absolute Galois group, it's no longer faithful. It's a faithful as a representation of the Galois group of K over F. But it's an irreducible representation of the Galois group of F tilde over F. So that is rho E, right? I wanted to say that from from a primitive solvable extension E over F of degree L to the N, I obtain a pair. This is a pair consisting of E hat, right? That's the second component, and rho E. Rho E, I'm thinking of it as a representation of the absolute Galois group on an n-dimensional FL vector space, namely this N. And it's an irreducible representation, right, of degree N. It's an FL representation. Why is it an FL representation of degree N? Because the degree of E over F was L to the N, and therefore this minimal normal subgroup N is an FL space of dimension N. So this is the summary of what we had done last time. To E over F, we attached a pair consisting of an irreducible FL representation of degree N and, and an extension, E hat. Now, E hat, what is it an extension of in this thing here? It is an extension, I'm thinking of it as an extension. You take the kernel of rho E, that's K. Take the fixed field of the kernel rather, right? K is the fixed field of the kernel of rho E, and this E hat is an extension of this K. What kind of an extension? It's an elementary abelian extension of exponent L and of degree N, right? So, okay. Moreover, this extension is not just an abelian extension of K, but it's also Galois over F. Okay, it's Galois over F, and therefore I get this short exact sequence. And rho E is nothing but obtained from the conjugation action of this on this when I think of this as a quotient of this absolute Galois group, right? So this is the pair rho E, comma, E hat attached to the extension E of F, which is a primitive solvable extension of degree L to the N. Now what we have is a sort of converse. Not sort of, I mean, it's a precise converse. So what is the converse? It says that suppose I have a pair, rho, comma, D. What kind of a pair? Consisting of an irreducible representation rho of the Galois group of E F tilde over F on some FL space capital N of dimension little n. So that's what rho is. Huh? These are representations of absolute Galois groups are absolutely everywhere. These are things which come up all the time. So here we are not looking at representations over the field of complex numbers or over some field of characteristic or over some other algebraically closed field. We are looking at representations over this prime field FL. Okay, so the field F is given to us. We have the absolute Galois group of F, and because we have also chosen F tilde, which is separable algebraic closure of F, and rho is an irreducible representation of this Galois group of F tilde over F on an FL space capital N of dimension little n. Moreover, this has to have solvable image. That's very important. The image is a subgroup of GLN of FL, right? I mean, the group of linear maps from capital N to itself can be identified with GL little n over the field FL. So it can have many subgroups which are not solvable. But we want the image of this representation rho to be a solvable group. Why do we want it to be solvable? Because ultimately we want, from such a pair, I have not told you what D is going to be, but once I've told you what D is, I'm going to say that I'm going to reconstruct an extension E of F. That extension is going to be not only primitive, but I want it to be solvable as well. And it is ultimately in order for that E to be solvable that I'm choosing a representation with solvable image. Okay? So rho is just an irreducible representation of the absolute Galois group of F on an FL space of dimension n with solvable image. That's what rho is. Okay, that's the first component. That tells me what rho is, right? Now I have to tell you what this D is. What is D? Now, D is an n extension of the fixed field K of the kernel of rho. So let's understand this slowly. What is the fixed field of the kernel of rho? Now, the kernel of rho is, of course, clear what it means. It's this, after all, rho is a homomorphism from the Galois group of F tilde over F into the group of FL linear maps, FL linear automorphisms of the vector space capital N. Anyway, it's a homomorphism between two groups, and therefore it has a kernel. So that's the kernel. And the kernel is a subgroup of this absolute Galois group. So I can take the fixed field of that kernel, and that is being called K. Now, by the very construction, this K is a finite extension of F because why is it a finite extension? It's actually a Galois extension, and the Galois group is equal to the the image of rho, right? Because that's right. Right? You just have to think of whenever you have a homomorphism from the absolute Galois group and you look at the kernel, then, and you take the fixed field of the kernel, you get a Galois extension of the base, and the Galois group of this extension is, of course, the quotient of the absolute Galois group by the kernel, right? So that's, and in here, the quotient of the absolute Galois group by the kernel, of course, is equal to the image of that representation. So this K is a Galois extension of F, and the Galois group is equal to the image of rho. That's clear. Now, so I've told you what K is, right? The second component, D, is an N extension of K. So what is an N extension? By that, I just mean that it's a Galois extension of K. So D is a Galois extension of K. And the Galois group of D over K is given to be isomorphic to this group N. What was N? N is this space, FL space of dimension N, little n, on which the absolute Galois group is acting, right? Anyway, it's a group, and I'm just asking for N extension, Galois extension D of K, whose Galois group is isomorphic to this N. Okay? So, but that's not the end of the story about what D is. That's just the first thing about D. Okay? The next thing about D is that it should be Galois over F. Now, you all know that when I have a Galois extension of a field and a Galois extension of that extension, the big extension, the top extension, doesn't have to be Galois over the bottom extension, bottom field, right? The examples are plenty. So you have to put in this requirement that D should be not only Galois over K, which it is by definition, but I require it to be Galois over F. Now, once it's Galois over F, you get a short exact sequence, because you have, let me see if this pen can be made to work. Let's see. You have, what here? Oh no. You have D here. No, it's not really working. It's not working. Anyway, so you have D, which is a Galois extension of K, which is a Galois extension of F. And I want D to be Galois over F. So as soon as this requirement is met, I'll get a short exact sequence. The kernel is going to be the Galois group of D over K, and the quotient, the middle term, is going to be the Galois group of D over F, and the quotient is going to be the Galois group of K over F. Now, as soon as I have a short exact sequence, I get a conjugation action of the Galois group of K over F on the Galois group of D over K, right? Just as we had it here. Just a little while ago, we had this short exact sequence, and we had the conjugation action corresponding to this short exact sequence, right? So here also I want this D to be Galois over F, and therefore I'm going to get a conjugation action of the Galois group of K over F on the Galois group of D over K. Fine. So such that the requirement now is that the conjugation action, that the conjugation action of the Galois group of K over F on D on N should be given by rho. What this means is, see, we are already in some sense given one conjugation action of the Galois group of K over F of this on this. That's rho, more or less by definition, because this is the image of rho. This here is nothing but the image of rho. And rho, of course, acts on this. So, the final requirement is that this conjugation action should be the same as the given action. Now, I've told you what, I've completed the list of properties that the pair rho D is supposed to have. Okay, So we will now show that this rho d uniquely determines up to F isomorphism, a primitive soluble extension E of over F of degree L to the N. Up to F isomorphism, there's a unique such extension. This is what we are going to show next. Of course, there's a unique extension. Well, that's not a... you have to say what this extension is expected to, what property this extension is expected to have. Unless I tell you what property E over F is supposed to have, this is meaningless. This rho gives me an E, rho comma D gives me an E. I could take any E and claim that, yeah, this is what rho comma D gives me. You have to say what property this E has to have. And the property is that the E, being a primitive soluble extension of F of degree L to the N, will give me this pair rho E comma E hat, as in the previous paragraph, right? So this new pair that I get, I start with one pair, I produce this extension E, and then I get this pair from E. So that new pair should be the same as the old pair, or in fact, isomorphic to the old pair. So this is the property that E is expected to have with respect to, or in relation to, this pair rho D from which I start. So, and of course, another thing that we expect is, suppose I start with a primitive soluble extension E over F of degree L to the N. Then I get this pair rho E E hat. I get this pair, right? As in the previous paragraph. Now, it's a kind of pair which I've been describing in this paragraph. It's a pair like rho D that I'm discussing here. And pairs rho D also give me a primitive soluble extension of F of degree L to the N. So I should get back the same E from this pair, right? That is another thing that we need to verify. In other words, we are sort of constructing a bijection between the set of primitive soluble extensions of F of degree L to the N. On the one hand, that's one set, and the set of pairs rho comma D, where rho is an irreducible FL representation of degree N of the absolute Galois group of F with soluble image. And D is an elementary abelian L extension of degree L to the N of K, which is the fixed field of the kernel of Rho, and this D is required to be Galois over F, and the resulting conjugation action of the Galois group of K over D on the Galois group of D over K is required to be the given action rho. So these pairs, you see, you might say that, the left-hand side, which just consists of primitive soluble extensions of F of degree L to the N, that's a much simpler set. And the right-hand side, which consists of these pairs rho comma D, that looks a very complicated kind of a set. First of all, you have to cook up irreducible representations of the absolute Galois group over the field FL, and then you have to cook up elementary abelian L extensions of the fixed field of the kernel, etc., etc., and which are supposed to satisfy some hypotheses, some conditions. But one should realize that the left-hand side, although it can be described in fewer words, is much more difficult to compute, or I mean, we don't know anything about it, whether this is empty, not empty, how many elements it has, or what kind of elements. Whereas the right-hand side, we will see, I mean, the side consisting of these pairs is something which we will be able to explicitly write down for the kind of fields which interest us. And the fields which interest us are these P fields, which we have also sometimes called locally profinite fields. These are fields which are complete for a discrete valuation with finite residue field. Of course, this discrete valuation should not be trivial. Okay, so let's get going in the sense that let's show that this kind of pairs here give you the kind of extensions that we were talking about. So for that, this here at the bottom, and which continues to the top of this page, is a sort of highbrow proof that what you get is it's a proposition which is used in the proof. It's not a proof of this bijection yet. It's the main ingredient. So, and it's a purely group theoretic result. But it's a little highbrow. Let me stick to this lowbrow statement, which is the statement 11 here on the top of this page now, right? So I'll just come back to it and let me see if there are any questions. This is the time to pose any questions you may have. Okay, there are no questions. So let's come to this lemma or proposition 11. It doesn't have anything to do with fields and their extensions. It's purely about groups and their modules. So let's look at this. So what does it say? So we are looking at a finite solvable group, right? It's not even a subgroup of a symmetric group or anything. It's just an abstract finite group which happens to be solvable. And then this M is a faithful, simple FLG module. So let me explain that. What does that mean? So that means that M is a vector space over the field FL. That's the first part. And the second part is that I'm given a homomorphism from G to the group of FL automorphisms of M. Every vector space has the group of all linear automorphisms of that vector space, right? And so an FLG module is just an FL vector space with a homomorphism from G to the group of linear automorphisms of that vector space. The vector space is being called M. Now, that's what an FLG module is, right? I mean, for that, G doesn't have to be a finite group or even a solvable group. And I haven't told you what a faithful or simple module is. So let's come to that. So G being any group, so I've told you what an FLG module is. It's going to be called faithful if that homomorphism is injective, right? That's a simple concept. Faithful if that homomorphism is injective. Simple is somewhat simple is also, I mean, it's not all that hard to say what simple is. So what it means is that whenever I have a vector space and a group of automorphisms, I said a group of automorphisms. I didn't say the group of automorphisms, right? And the group of automorphisms that I'm looking at is the image of this G. I'm given a homomorphism from G to the group of automorphisms of this vector space, and the image is a group of automorphisms of this vector space. So whenever I have a group of automorphisms of vector space, I can ask whether there are some subspaces which are stable under that subgroup. So which means that every element in that subgroup, of course it's an automorphism of the vector space, should take that subspace that I'm looking at into itself. Every automorphism in that particular subgroup that I'm looking at, right, should take that vector subspace that I'm looking at into itself. Then we will say that that subspace is stable under that group of automorphisms. There are two subspaces which are always stable under any group of automorphisms, and those are the subspaces, the trivial subspaces and the improper subspace. The trivial subspace is the subspace consisting of the origin alone, and the improper subspace is the subspace consisting of the whole space. So those two are always stable under any group of automorphisms. Now, if for the group of automorphisms that I'm looking at, that's given to me, there is no other subspace of the vector space which is stable under that group of automorphisms, of course, then I say that this vector space or this module, right, is a simple module. It's a module over that group of automorphisms. So that's a faithful, simple module, right? So what I'm given now is a final. So let's come back to the statement and look at the hypothesis. I'm given a finite soluble group G and a faithful, simple FLG module, which is called M. Okay. Now it says that if I have an extension L of G by the G module M. So what does that mean? That just means that L is a group and I'm given a short exact sequence like this. A short exact sequence like this, which means M, capital M is a subgroup of capital L, and the corresponding, it's not just a subgroup, but a normal subgroup, and the corresponding quotient is the group L, a group G. Okay, so that's what, but that's not all. Whenever I have this short exact sequence, I've explained this several times today, that there's a quotient of the, there's an action of the quotient G on the normal subgroup M. So the requirement is, but I'm already given an action of G on M, namely because M is a FLG module. It's already, which means that I'm given an action of G on M. And here in the action arising from the short exact sequence should be, that's called the conjugation action, and it should be the same as the given action. That's what is meant by an extension L of G by a G module M. It's not by an arbitrary group, but M is already given to you with an action of G, and I want a short exact sequence in which the resulting conjugation action is the given action. Okay, so the statement 11 is, so these were the hypotheses that this is the kind of thing that I have. I have a finite solvable group G, I have a faithful simple FLG module M, and I have an extension L of G by the G module M. These are the things which are given to me. And having an extension means having a short exact sequence like this, in which the conjugation action is equal to the given action. And the proposition is saying that any such short exact sequence actually splits. Okay? So what that means is, what does it mean for a sequence to split? It means that there's a homomorphism from G to L. Normally you don't have a homomorphism from a quotient to the big group of which it is a quotient. For example, you have Z mod P squared Z, let's take a prime P, and you have Z mod P squared Z, and you have Z mod PZ as a quotient. Now there's of course no homomorphism from Z mod PZ to Z mod P squared Z, which is a section of this projection. The projection is from Z mod P squared to Z mod P. And what does it mean for a homomorphism from Z mod P to Z mod P squared to be a section? It means that when I apply this homomorphism, when I apply this purported section, and then I apply the projection from Z mod P squared to Z mod P, I get the identity map of Z mod P. That's what a section would be. So this here is saying that there's always a section. So the point is that short exact sequences sometimes have sections and sometimes don't. Those which have sections are said to split, and they're of a special kind. They are a special kind because then the middle thing, the extension, is a semi-direct product of the quotient and the sum. It's a semi-direct product for which action? For the conjugation action, right? So in some sense, if a short exact sequence splits, then it's the simplest possible extension, namely the semi-direct product. It should actually be called the neutral extension because it's the neutral element in the group of extensions. In some sense, if you are given a group G and a G module M, then you can define the notion of, meaning I've already defined the notion of an extension of G by the G module M. I've defined this notion. Now the point is that you can also define a notion of isomorphisms of such extensions. And the point is that isomorphism classes of such extensions themselves form a group. It's not completely obvious, right? It's a set, of course, but it's a set which has a natural structure of a group. There's, it's like, like if you were to take the set of all bijections of a given set, then it's naturally a group. And here, it's not quite the same kind of thing. It's slightly deep. It's much more deeper. But that's what you need to know at some point, that once I've fixed a group G and a G module M, and I look at extensions of G by the G module M up to isomorphism, then there's a natural structure of a group on this set. You might ask, what is the neutral element for this section, for this group structure? And the answer is the semi-direct product. So if you recall what a semi-direct product is, it's the underlying set is the direct product of G and M. Normally, I would tend to write M on the left, so it's M cross G as a set, but the product of M1 G1 and M2 G2 is defined. It's not the diagonal product, so to speak, is not M1 M2 comma G1 G2. It's M1 times G1 acting on M2. That's the first component. And the second component is, of course, G1 G2. So that is the semi-direct product. It's an extension of G by the G module M. One is to check that. And then you have, of course, so it's an element of that set and of that group, and it's the neutral element for that group structure. Okay. So, so that's the first part. Any such extension splits, meaning the semi-direct product is the only extension. And the second part is any two sections are conjugate by an element of L is written here, but I could say that it's conjugate by an element of M, in fact. Okay. Now, so this proof here, right? It relies upon this previous statement, number 10, which I have not discussed. But there are direct proofs of this statement without referring to these cohomology of groups, and they can be found in these sources here, right? So what is the I mean, what is the content of this statement here? It says that if your G is finite and soluble, and if your module is faithful and simple, then the only extension is the semi-direct product. That's the first part. And the second part is, so for the semi-direct product, it has many sections. Okay? I mean, in fact, it comes with a canonical section. And the thing is, the interesting thing here is that not only does the semi-direct come with a canonical section, the set of sections from the quotient to the semi-direct product can itself be made into a group. And that group is called H1GM. The earlier group that I described, the one of which the semi-direct product is the neutral element, is denoted H2GM. So whenever you have a group G and a G module M, you have a whole sequence of groups. You have H0 or H0 GM, then there's H1, H1GM, there's H2, H2GM, there's H3, and so on. Now these lower cohomology groups, namely H0, H1, and H2, they admit very concrete descriptions. And I've told you what they are for H1 and H2. H1 is a group of all sections of the semi-direct product, the group of all sections. And H2 is actually the group of all extensions of G by the G module M. I should have also told you what H0 is. H0 is just the set of invariants, the group of invariants for this action of G on M. So it's the set of all elements of the module M, on which every element of the group G acts trivially. So G acting on M, little g acting on little m is equal to little m. That is what this Yeah, for example, if you're Galois extension, then you know and you have the Galois group, then the set of invariants of the Galois group is the base field, right? So here you have a subgroup of M, which is going to be the set of invariants for the action of G on M. So that's H0 GM. And I've told you now what H1 is, what H2 is, and this is followed by H3, H4, and so on. So there's a whole theory of group cohomology, which is extremely useful in various contexts. Okay. So now this was pure group theory up to all this, right? There's no arithmetic or even field theory here. So now we are going to come to the field theory part. So here's the statement. So this is the converse. So you have to recall the context. We have a field F. We have a primitive solvable extension E of F of degree L to the N. And to such an extension, we produced a pair. To such an extension, we attached a pair, rho E, comma E hat. This belonged to the set of pairs rho, comma D, satisfying certain conditions, right? I want to say that this is, so by definition, the map attaching to the extension E, the pair rho E, comma E hat was, well, I mean, it's a map for the time, okay? And I want to show that it's a bijection. So in order to show that it's a bijection, I first need to produce a reciprocal map. So producing a reciprocal means to a pair rho, comma D, I have to attach a primitive solvable extension E of F of degree L to the N. This is what I need to do. So, remember, attach meaning it's not an arbitrary attachment. It's not an arbitrary correspondence. It should be such that when I take rho E, comma E hat, I get back rho, comma D, right? So it has to be this new map that I'm trying to construct has to be reciprocal to the old map which I had constructed earlier, attached to rho E, comma E hat, right? Okay. So rho, comma D is given to me. I have, of course, the kernel of rho, and rho being an irreducible representation of the absolute Galois group, I have the fixed field of the kernel of rho. I'm calling it K. So then, of course, I get, now D, by definition, was an extension of K, which is Galois over F, etc. So I have this short exact sequence. What do we know about this short exact sequence? I know that so I know that I'm in the hypothesis of this proposition here. Okay? Which is to say that this, first of all, yeah. That this group is solvable, which is true by hypothesis, that this is an FL representation of this group, which is irreducible, which is also true by hypothesis, etc. So I get exactly the kind of short exact sequence which this proposition 11 is discussing. And therefore, by the purely group theoretic results that I've discussed, this short exact sequence has a splitting, and not only does it split, any two splittings are conjugate by an element of the subgroup Galois group of D over K. Now I take a splitting, which is of course a map. It's a map where, it's a map here, which is a map here in this direction, right? From the quotient to the whole group, to the total group. And so I get a subgroup of the middle group. Now, when I have a subgroup, I can take its invariance. This is a subgroup of the Galois group of D over F, right? So I can take the fixed field under that subgroup. So that subgroup, what is it going to be like? It's going to be a complement of this. So in particular, the index of that subgroup is going to be L to the n, because this group here is of order L to the n. So the index is L to the n, and therefore, when I take the fixed field, it's going to be of degree L to the n over F. So I've got an extension, let's call it E. E is the fixed field of the image of any section. Take any section, take the fixed field, call it E. So we have to now, so in order to construct this E, what have we used? We have used the fact that there's a section. Now we are going to use this other fact that any two sections are conjugate by an element of this here. Both these things were part of the proposition 11. So if they are conjugate, any two sections are conjugate, implies that any two groups that I get here as images of those two sections are going to be conjugate in this big group, or it comes to the same to say that they are conjugate by an element of the Galois group of D over K. And therefore, because these subgroups are conjugate, their fixed fields are also going to be conjugate. So that gives me the uniqueness of E. But why is it soluble and why is it primitive? E over F, why is it? It's also of degree L to the n that we have seen, because that's the order of this group. But why is it soluble? It's soluble because it's contained, for example, in D over F, and D over F is solvable. This group, Galois group of D over F, is a solvable group, right? This is by, okay, why is it a solvable group? Because this quotient is solvable by hypothesis, and this, of course, is solvable because it's a commutative group. So that means that that E over F is solvable. And why is it primitive? Well, it's primitive because, again, because you can see that it's the, it's, how should one say it? Well, ultimately it will come from the fact that this representation of this group is irreducible. So, and that's part of the statements here, okay? Because this is because this subgroup is a maximal subgroup. Yeah, that's so. There's a unique conjugacy class of complements, and they are all maximal subgroups. So maximal means the fixed field is a primitive extension. Okay, so now what I've done is I've proved the following. Sorry, there's something in the chat box, I believe. Let's see. No, it's not a chat box, it's something else. Oh, it's some other something. Okay, forget about it. Okay. Let me summarize. Yeah, here it's a summary here. I mean, it's kind of written here. So what is the summary? The summary is that if I'm given a field F and a prime number L, then every primitive solvable L extension E of F is uniquely determined up to F isomorphism by E hat over F. E hat is the Galois closure of E over F, right? In what sense have we proved this? We have proved it, right? We have proved it because we said you look at E hat over F, it's a Galois extension with Galois, let G be the Galois group, then it has a unique, G has a unique minimal normal subgroup. You take the invariants under that minimal normal subgroup, you get this K and everything, right? You get the whole shebang. So that is the first part. Now, so the second part would be when to characterize these E hats which are obtained from primitive solvable L extensions. What kind of E hats do I obtain? If I characterize them, then I have sort of characterized, because these are E is uniquely determined from E hat, and if I characterize the possible E hats, then of course I have characterized the possible E's, and which is what we aim to do. So the characterization of E hat is as follows. So given some extension D of F, it's of the form E hat, if and only if this D is an elementary abelian L extension of the fixed field K of the kernel of an irreducible FL representation rho of this with solvable image such that D is Galois over F and the resulting conjugation action of the Galois group of K over F on the Galois group of D over K is given by rho. This is what we have been repeating several times, that this is the requirement for this. I mean, this is encoded in this pair rho comma D. Okay, in terms of parameter rho comma D, this group is just given by the semi-direct product of these two things. Okay, so that's that sort of finishes off the mathematical part of today's lecture. Now here is some sort of description of, so what you can do is you can specialize. You can take L equal to 2, which is the smallest possible prime, of course, and you can take N equal to 2, which is the smallest integer strictly greater than 1, because N equal to 1 we have already seen, right? I mean, this is also being done in the tutorials. So N equal to 1 is not, well, it is exciting, but if you want to go beyond this, the first case that you should look at is n equal to 2. So these will, of course, be primitive extensions of degree 4, so primitive quartic extensions. So given a field F, what can you write down? All primitive quartic extensions. And I'm not saying that they should be solvable, because, I mean, if it's a quartic extension, then the Galois group is going to be a subgroup of S4, and S4 itself is solvable. So every quartic extension is automatically solvable, just as every quadratic extension is automatically Galois, right? I mean, provided, of course, it's separable. So I'm looking at primitive quartic extensions. Primitive already presupposes that these are separable, and quartic means the degree is 4. So I'm given a field F, and I'm looking at, that looks a very simple sort of question, an obvious kind of question. Given a field F, I'm looking at, we're trying to find all degree 4 extensions of this field. For example, let's start with, okay, given a field F, you can try to enumerate all extensions of this by 1 degree at a time. So extensions of degree 1, of course, there's 1, and that's F itself, and there are no others. Extensions of degree 2, we are all talking about separable extensions. So if the field is of characteristic different from 2, then you just have to look at F star modulo F star squares, and non-trivial elements of this group will give you quadratic extensions. And their non-trivial elements are in bijection with the set of quadratic extensions up to F isomorphism. And if the field happens to be of characteristic 2, then instead of Kummer theory, you will use Artin-Schreier theory. So you look at F plus modulo P F plus. P is this map which takes x to x squared minus x, or x squared plus x. It makes no difference. You are in characteristic 2. So then you look at this vector space over F2, which is F plus modulo P F plus. And non-trivial elements of this vector space, or non-trivial non-zero vectors, give you separable quadratic extensions of your field F. So that takes care of degree 2. Degree 3. Now, degree 3, it's, first of all, F3 is a prime. And secondly, the group S3 is solvable. So every separable extension of degree 3 is solvable. So we can use our results about solvable extensions of prime degree. And we have parameterized them. If you go beyond degree 3, if you go to degree 4, then the first thing that would occur to you would be extensions which are, I mean, of course, you can get degree 4 extensions by taking 2 degree 2 extensions and taking their compositum. Or you could take a quadratic extension of a quadratic extension, right? There are these 2 obvious ways of making quadratic extensions, which is take the compositum of 2 quadratic extensions, which have to be, of course, linearly disjoint, right? For the compositum to be of degree 4. Or you could take a quadratic extension of a quadratic extension. And the resulting thing may be Galois, may not be Galois, whatever, but it's a degree 4 extension. It's a quadratic extension. But and these are not the only possibilities. You could have a quadratic extension which is not of any of these 2 types. And that comes to the same as saying that which doesn't have any intermediate extension of degree 2. I mean, if it has an intermediate extension, it'll have to be of degree 2 over your field F. So you can a priori think of quartic extensions which don't have any intermediate extensions, and that's the same as saying that they are primitive. So that is the first non-trivial case that you can think of for extensions of a field is actually primitive quartic extensions. Not even cubic extensions, because they are kind of covered by, they are automatically solvable and they are of prime degree, so they are sort of parameterized by something which is very simple, ultimately Kummer theory or Artin-Schreier theory. So this is the first case where it would seem that Kummer theory or Artin-Schreier theory are not directly giving you anything. Which case? It's of quartic extensions which are primitive. But fortunately, this is what we have discussed today. So so what this number 15 says is that primitive quartic extensions can be of two types. Those whose Galois closure is either the group A4 or the group S4. So now this is what you can see here. When I take the Galois closure, I'll get a subgroup of S4, which is what? Which is primitive. That's one of the things. And which is solvable. Solvable is automatic because it's a subgroup of S4. But then, so one has to look at what are the primitive subgroups of S4. And the answer is there's only A4 and S4. Okay. So, so this here, of course, up to 15, number 15, we were working over arbitrary fields. Now, we can specialize this to fields of interest to us, for example, the field Q, and you could ask for primitive quadratic, not quadratic, quartic. Primitive, what was this then? Primitive quartic fields, which are, by definition, primitive quartic extensions of Q. Now, here is the interesting thing. So, instead of Q, which has infinitely many of them, Q2 has only finitely many primitive quartic extensions, and people have sort of determined them completely, and they are, there's a unique one for which the Galois group is A4. Here we saw, what did we see here just a moment ago? That if you have a primitive quartic extension, the Galois group is either A4 or A6, the Galois group of the Galois closure. So as far as Q2 is concerned, there's a unique primitive quartic extension whose Galois closure is A4, and it's given by this polynomial. Similarly, there are three quartic extensions which are primitive and whose Galois closure is S4, and these three are given by these three polynomials. So this is something which people must have done some time ago, but there's also a paper by Vail, I think it's called Exercice Diadique or something. Exercice Diadique. It's in the invention is maybe in the 70s or something. So Vail is Andre Vail, and he lists these polynomials explicitly, right? But I'm sure it must have been done much earlier by other people. Okay. So let's okay, so now let me tell you what we are going to do in the remaining 3 weeks. So we are going to look at the local theory, which means that the base field is going to be our P field, a P field F. And we, just as here, Q2 was just this first possible case, right? But instead of Q2, we could just take any P field, and we would like to parameterize all, not just primitive quartic extensions, but all primitive extensions. One of the things which happens for a P field is something which I've already explained maybe 2 or 3 times, is that every finite separable extension is solvable in the sense that when you take the Galois closure, the Galois group is a solvable group. That comes from the fact that you have this ramification filtration for which you know what the successive quotients are. They are either cyclic or elementary abelian, and therefore everything is fine. Okay. And so, in order to solve this problem for an arbitrary P field, we will use this parameterization which we have obtained today in terms of these pairs. So rho comma d, right? So there has to be first, we have the set of all e's. We were asking what are the possible e's. We said, oh, they are in bijection with the rho comma d's. Now we have to say what are the possible rho comma d's, meaning what are the rows, what are the d's for each row. So what are the rows have actually already been determined by somebody called Koch, and maybe this is what we are going to look at next week. So given a P field, we are going to look at, even before we do that, we are looking at extensions of degree L to the n, right? But if this L is different from P, then such an extension is primitive if and only if n is equal to 1, right? Because you just, if it's, if L is different from P, then L E over F is tamely ramified, and we know what tamely ramified extensions look like, and in particular, it cannot be primitive unless it is of prime degree. So the really interesting case, the really interesting thing for a P field is when the degree of E over F is P to the n for some n. And therefore, we will need to look at rows which are irreducible representations of Galois F tilde over F into GLN of Fp. P is the same as the P residual characteristic of this F. And this, the set of all such rows, such rows have been determined by Koch in a paper, which is essentially what we are going to discuss next week. And then, then what are we going to do? Okay, so Yeah, so then we will have to determine the possible Ds for each row. For C, we have to construct these pairs rho comma D. So the next week we'll explain what possible rows there are, and the week after that we'll tell you what possible Ds there are. Okay, and the final week we are going to put everything together and describe all primitive extensions of degree p to the n of a p field f. P field f. So given a p field f and an integer n, we are going to describe primitive extensions of E or of degree p to the n. So this is what the plan is, and it so happens that I've written all this up, and you can either look at my papers in the archive, or I mean I'll keep on sharing the papers when each week, just as I've done it this week, and we'll go on from there. Right, so I finished for today. Let me see if there are any questions.
Yes, sir. Sir, you have defined in real 11 that
Are there any
any
questions?
extension.
No.
Yes, sir.
Okay. Right.
Yes, no, sir. I have a question. I have a question. Sir, in reality 11, you have defined an extension L of